check. Okay, guys, returned midterm 2 is on the stage. You'll have time before class and after class to pick it up. Returned homework 7 is on this table up here.
It's a quick question.
Yeah.
You know who is grading this midterm?
That information will be posted on. Will everyone please take your seats? We've got to start class on time because we got a lot of material to cover. Please take your seats. Please take your seats now. Papers will still be here at end of class. You'll have another shot at it. Okay. Okay, let's just look at the web page for a second. PA 5 is due Sunday, 10 p.m., which means it closed Monday. Is that good enough or not? Are we finishing up? How many people are still working on PA 5? And okay, good. I expected that I gave you the rest of this weekend to work on it. But are you going to be done by Monday morning at 10 a.m. when I close the door? All right, I'm willing to go one more day, but I can't go any longer than that because the grader has to have it, and I have to have it back before I have to turn in grades. And it takes some time to get this done. So I'm going to give one last day to PA 5. Okay? So that means it'll be due Monday, 10 p.m. It'll close Tuesday, and I'll give it to the grader sometime Tuesday afternoon. Okay? That's the way it's got to be. That'll give you at least one more day of help from the TAs. That's Monday. You'll have Monday to get some help if you haven't already gotten help. Whatever you do, get help early. I guess you all know what happens when things get pushed back into the past or into the future. You get a big crowd of people in my office, outside my door during office hours or in the labs, and it becomes very hard to get any help. So, I don't know, I guess I should have given this speech on day one. I did give this speech on day one, now that I think about it. Don't wait to get help, but just figure out a way to get help. Piazza is a good way if you can't go see somebody. Okay, so where were we last time? We were talking about heapify. So we're talking about the heap data structure. What is the heap data structure? It is an array with two attributes, length and heap size. Length is fixed, heap size is mutable, can go up or down. Can't be any larger than length. And three helper functions, parent, left, and right. And parent, left, and right helper functions implement a mapping between that array and an almost complete binary tree. And the number of nodes in the almost complete binary tree is heap size. So I drew some pictures last time. Here's a typical example of one. And there's one more thing that it must satisfy. One of the two heap properties. A max heap satisfies the max heap property. A min heap satisfies the min heap property. Max heap property, for instance, says that every node stores a value that is greater than or equal to the value at each of its descendants. Okay, that's just another way of saying the same thing. I said the value at a node is greater than or equal to its left child, and it's greater than or equal to its right child. That's the max heap property. But since that's true at all nodes in the tree, it's true in an entire subtree. So the subtree rooted at index 2 is itself an almost complete binary tree, you notice. Actually, this one happens to be complete. It's filled at all levels, including the bottom. And that almost complete binary tree, at all points, satisfies this heap property. That is to say, every node's value is greater than or equal to all of its descendants' values. Likewise, the subtree rooted at 3 is itself an almost complete binary tree on fewer nodes. Notice it is filled at all levels except the last. The last has just, the bottommost level in this tree has just one node in it. Okay? That's what a heap is, heap of phi has as precondition that the subtree rooted at the left child of a node. Well, first of all, we call heap of phi on an index I. And the precondition is the subtree rooted at its left child is a valid heap. That means max heap property is satisfied at that node and at all the descendants. So the value here is greater than or equal to all its descendants. Likewise for the right subtree of I. The goal, okay, but the heap property may or may not be satisfied at node I itself. Okay, and the goal is to cause the max heap property to be satisfied at I. That's the goal of heapify algorithm. So how do you do that? Well, it's very simple. I mean, first of all, if the heap property is already satisfied at I, you should do nothing, right? You should not bother to do anything, right? But the call to heapify at least certifies for you that the subtree rooted at I is a valid heap. But if it's not a valid heap, then why isn't it? It's because the value at I is less than one or both of its two children. So how do you fix that? Figure out which of the two children is greater. And then swap the value in I with the value in that child. So, for instance, suppose the larger, amongst these three, the largest value is stored at the left child. You swap I and L. Swap the parent I with the left child L. When I say swap, I mean swap the values. Swap the array contents. That establishes the heap property at I. But what does it do that could upset? What does it undo, possibly? You just put something in L that's smaller than what it used to be. What if that value is smaller than one of its two children, the grandchildren of I, the left grandchildren of I? Then you have a violation of heap property at L. But you still have the valid heap property at the two grandchildren, the two left grandchildren, the left child of the left child and the right child of the left child. You have that because you had it before. So a recursive call to heapify on the left child will remedy that situation. So heapify is a recursive algorithm. It looks for a violation of the heap property on the assumption that the two subtrees are themselves valid heaps. If it finds one, it does a swap and calls itself recursively on the node on which with which it swapped. So heapify ends up walking down a line of ancestry within the tree. And it stops when either there's no more violation of the heap property, you just get lucky and then the node you're at already satisfies the heap property with respect to its two children, or you reach a leaf. You reach a leaf and it has no children, so there's no possibility of a violation of the heap property. That's how the heapify algorithm works. Okay? Now that I've just told it to you verbally, do you think you could write it? Well, I won't bother to write it because I've already written it to save time. There it is. Okay, I'll put this over here. Okay, so precondition is that the subtrees at left I, here's I. Oh, I've got to switch pictures now. Here's I, here is left child of I, here is right child of I, and the preconditions are that these two subtrees are valid heaps. That is, they satisfy the max heap property. All right, so let L be left eye and R be right eye. That's just assignment of a local variable L and R. Now ask, is L less than or equal to heap size A? By the way, when the book writes this, they use, instead of kind of array notation, they use, field access notation, A dot heap size. Okay, fine. It looks more like Java, what they write. If L is less than or equal to heap size, why do you bother to ask that? Well, L is twice I, right? And for all you know, I is a leaf and it has no left child. In which case, if you calculate 2I, you get an index that could be outside the array, right? Twice I might actually be outside the array, or it might be inside the array, but to the right of heap size. So you don't want to consider nodes that aren't even in the tree, whose indices are greater than heap size, because they're not considered to be in the tree. So that's why we test this. If L is less than or equal to heap size, in other words, if there really is a node there, and there's a violation of the heap property between left child and right child, so the left child is greater than the parent, set largest equal to L. So far, largest is the index that stores the larger value. Okay? I'm sorry, else largest equals I. So after line 6, largest is the index of the larger value. If this is the larger, largest is L. If this is the larger, largest is I. Got that? So now I have to consider the right child. Again, if R is less than or equal to heap size, in other words, if there really is a node there, after all, this could be way down in the tree, and maybe this is the bottom level, and maybe this is where it stops. This is the rightmost leaf on the bottom level, and that guy exists, but that guy doesn't exist. But we check that by comparing R to heap size. If R is less than or equal to heap size, and there's a violation of, let's put it this way, AR is greater than A largest. So whatever is there is bigger than the bigger of these two. Then I put largest equal to R. Otherwise, I don't do anything. By the time I reach the end of line 8, largest is the index, I, L, or R, of the largest number amongst these three values in these three nodes. Okay? Notice all of that just took constant time because it's a couple of conditionals you test, a couple of assignments. It's all constant cost so far. Okay, and then the final conditional. If largest is not equal to I, because if largest is equal to I, there's nothing to do, right? The heap property is already satisfied at I. The call to heapify AI merely certificates, I don't know if that's the right word, but it guarantees that the heap property is satisfied at I. All right, but if largest is not equal to I, then I've got to do one of these swaps. So swap AI and A largest. If largest was L, then you swap these two. If largest was R, you swap these two. And then what? This is where the real work gets done. The recursive call to heapify, same array but different index, whichever one you swapped with. Okay, that's heapify. So what's the runtime of heapify? Well, I'm going to state the runtime in two ways. As a function of n, where n is the number of nodes in the subtree rooted at I. I'm also going to state it in terms of the height of that subtree. So T of n is the worst case runtime of heapify when run on a subtree, that's the subtree rooted at I, consisting of n nodes. So n is the number of nodes in the subtree rooted at I. Well, what is it? The subtree rooted at I? Well, okay, let's just think about what's the worst thing that can happen with heapify. Heapify climbs down a line of ancestry in an almost complete binary tree. So the worst thing that can happen is it climbs all the way down to a leaf and then has to stop at that leaf. Because at that leaf, once you hit that leaf, that condition is false and that condition is false because there is no left child and there is no right child. So therefore, largest will be set to I. This condition will be false and you'll do nothing and no recurrence happens. So it has to stop once it hits a leaf. The worst case is you climb from index I all the way down to some descendant leaf. Oh, what's the height of an almost complete binary tree on n nodes? Does anybody remember? Nobody remembers. I suggest you guys remember this. What's the height of an almost complete binary tree with having n nodes? We can be very exact. It's floor log base 2 of n. Okay, theta log n, right? But it is floor log base 2 of n. So it's the height of the subtree rooted at I. As a function of n, it is floor log base 2 n. Maybe I should just go ahead and write that. And asymptotically, that's theta log n. Get rid of the floor, get rid of the base 2. I mentioned that because we're interested in asymptotic runtimes. If you want to state it, though, in terms of the height of that tree, it's just linear in that height, theta h. Okay, that's page 2. This is page 3. Let's go to 6.3. Build heap. Remember, a build heap is what takes an unordered array and makes a heap out of it. Build heap we'll simply call heapify in a strategic fashion. So how does it do that? Let me begin with an example and show you how we can organize a sequence of calls to heapify in such a way that when we're done, the whole array is a valid heap. So let's start. I won't give the values, just the indices. Let's look at the tree picture. Okay. Here's the tree picture of the heap. And let's say that we have an array with 12 slots in it, right? It's an array of length 12 this time. Oops. Get rid of that one. Okay. So here is the array picture. Here's A. Here are the 12 indices. One, 2, 3, 4, 5, 6, 7, 9, 10, 11, 12. Okay. There's the array picture, and I'm not going to bother worrying about what's in it. But the point is, this is an unordered array. Like we haven't ordered anything yet. So we can view it as a tree, but it's not a valid heap yet. Well, what can we say about the subtrees of this tree? Which subtrees are already known to be valid heaps? Can somebody say? Are there any subtrees that are automatically valid heaps? Leaves. Why? Because the leaves have no children, and therefore no violation of the heap property is possible. So that's a heap, 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 and that's a heap. Okay? So let's see. I don't need to call heapify on 12, 11, 10, 9, 8, or 7, do I? I should call heapify on 6. Why should I call heapify on 6? Because its left subtree is a valid heap. Its right subtree doesn't exist. So if I call heapify on 6, so first of all, my call to heapify on 6 will succeed because it satisfies the preconditions of heapify. The left subtree is a heap, and the right subtree, well, non-existing is just as good as, it doesn't exist, right? So there's no violation, there can be no violation of the heap property there. So I can call heapify on 6. Can I call heapify on 5? Yes, because its left subtree and its right subtree are valid heaps. Therefore, the call to heapify on 5 succeeds because it satisfies the preconditions. Can I call heapify on 4? Yes, I can. It satisfies the preconditions. So by the time I return from that call to heapify on 4, this will be a valid heap. All right, so can I now call heapify on 3? Yes, as long as I do it after I've called it on 6. Because after I call it on 6, this is a valid heap. This being just one node is a valid heap, so I can call heapify on 3. The preconditions are satisfied. Can I call heapify on 2? As long as I do it after I called it on 4 and 5, then the precondition for calling it on 2 will be satisfied. And then this will be a valid heap, and this will be a valid heap. And then I can finally call heapify on the root. So this is the strategy. Back through the array, but skip the indices that belong to leaves. So that would be 12, 11, 10, 9, 8, 7. So these are the leaves, and these are the internal nodes. And these nodes, these leaves, you need not call heapify on. So just back through the array starting at the rightmost internal node. So call heapify 6, then 5, then 4, then 3, then 2, then 1. So I just need a loop. So here's the build heap algorithm. It's very short. Well, first thing you should do is set n to be heap size A, and set heap size to be length of A. Okay, that's step 1. So, you read this from right to left, right? Length doesn't change. Heap size does change. So initialize heap size to be length. We want to order the entire array as a heap and give that to the local variable n. Then a loop. 2 for I going from index of the rightmost internal node. Well, what can we say about the rightmost internal node? It is the parent of the rightmost leaf. The parent of the rightmost leaf has index, in this case 12, but in general index n. What was the formula for parent? Does anybody remember? So remember the parent formula? Right, floor n over 2. So floor of an index over 2 is the index of the parent. So start I at the parent of the last leaf. Why start at the parent of the rightmost leaf? Because that's the rightmost internal node. And you don't want to call heapify on any of the leaves. That's wasted time. So for I equals floor n over 2 down to 1, So you stop at the leftmost index. 3, heapify AI. That's it. That's build heap. All right. I have a whole bunch of notes here that go into the runtime of build heap. Worst case, runtime of build heap on an array of length n. Is T of n equals, anybody care to guess? That's a good guess. Unfortunately, it's wrong. Well, it's big O n log n, but it's not big omega n log n. So your asymptotic bound is an upper bound, but it's not a tight bound. It's obvious that it's no worse than n log n because this call to heapify can be no worse than log n, as we just saw, and it's being executed, approximately 1/2 n times. So the loop executes theta n times, and the calls look like they're theta n. So that's how we got theta n log. The calls to heapify are theta log n, as we just saw. So it looks like this loop runs in time theta n log n. The reason that doesn't go through is, remember, the cost of this is not theta n. N here stands for the length of the array. N in our analysis here stood for the number of nodes in the subtree rooted at I. And that changes from one call to heapify to the next. The first few calls to heapify are on, the height is just 1. Then it becomes 2. And then it gradually grows to be a call to heapify. Only the last call to heapify is on a tree with n nodes in it. So this is actually better than n log n. And this is what it is, theta n. Now, I have a lot of pages of notes that explains and proves rigorously that T of n is theta n. But guess what I'm going to do? I'm going to skip it. Because if I don't skip it, we're never going to get anywhere in this class because they stole time from us, remember? And they didn't lower your tuition either, did they? I hate to bring up that touchy subject. But they took time away from us just so that they could... I should stop complaining. Did I complain about this already? Not enough? I don't know who to yell at. There's nobody to yell at. That's what's so infuriating. Okay, so see the proof in the book. This hurts me personally not to give you the detailed proof that the runtime of build heap is linear, it's theta n, not n log n. Why does it hurt me? Because that's, in my opinion, that's what this class is about, right? Trying to learn how to figure out the runtimes of algorithms. All right, but I got to do it, so it's done. All right, so now let's go to 6.4. So those are the hows. You now know how to make a heap out of an unordered array. 6.4 is heap sort. Heap sort is a really nice and efficient sorting algorithm based on the heap data structure. So here is heap sort. I'll just write the algorithm. And we'll analyze it. First, build heap. So the array A is now in heap ordered form. And that took theta n time. That took linear time to do. Just for simplicity, let n, at this point, n is, let's set n to length A. N is also heap size, okay? So we're trying to sort the array now. So what I'm going to do, so let's just stop for a second and think what we have when we have an array that's arranged as a heap. Maybe we should go back to this picture for a second. Okay, go nice and slow. There we go. Here's our first example of a heap. So the one thing you can know about the heap, it doesn't seem to be ordered very well, but the one thing you know must be true is the largest element is at the root, isn't it? And that's always at index 1 because of the heap property. So that's the one thing you've got working for you. The largest element is at the root. The idea of heap sort is to take that, and where does that largest element belong? It's in the leftmost position. It belongs in the rightmost position. When I say sorted, I mean sorted in increasing order. So the largest element should be just in the opposite direction. So what do? We simply do a swap. So we swap and put the largest element in the rightmost position. And now we need the heap property back. And we need to exclude that largest element from the heap. Otherwise, if we try to heapify now, what we'll get is that element, if we build heap again, we'll just get that largest element bubbling back up to the top. Okay? So you do a swap and then you decrement heap size. So that largest element is still in the array, but it's excluded from the heap. So everything about the remaining tree, where we've thrown away that last node, the rightmost leaf, as it were, it's all satisfying the heap property except possibly at the root itself. So a single call to heapify at the root will reestablish the heap property throughout that tree. So then the second largest element in the array is at the root. Swap that with the second to the rightmost element in the array, and then decrement heap size again. Every time we decrement heap size, we are excluding a number from the heap, but it stays in the array. So we're basically making the tree smaller one node at a time. Okay, that is what the purpose of this loop is. For I equals n down to 2, 3, or 4, swap AI with A1. The double arrow is my symbol for a swap. You know, you need a temp for that usually. So you do this swap and then exclude that largest element from the heap by decrementing heap size. Decrement heap size. So whereas heap size was equal to length initially, it goes down by 1 on each iteration of this loop. And then a single call to heapify on the root, that's index 1, will re-establish the heap property in the remaining nodes. Why is it just that one call to heapify? Because the left subtree is a valid heap because it was before. And the right subtree is a valid heap because it was before. What about that largest element? That's no longer in the tree. That was excluded when we decremented heap size. Okay. So I should probably trace this for you, but I won't. I think you can all do it, so I'll leave that as an exercise. Exercise. One exercise is to trace this on an example, and then two, actually write it down in like C or Java or something like that. Write this out and run it and test that it works. Go ahead. No, there's no particular advantage. If you wanted to sort it from greatest to least, to in descending order instead of ascending order, then you should use a min heap. Go the other way. The same operations, but on a min heap. That would sort it in decreasing instead of increasing order. Okay. So, first exercise is trace this on examples. Write down an array of length 10 or something like that. And then, as you're tracing it, draw the array every time on each iteration, and also draw a new picture of the tree. On every iteration, the tree has fewer and fewer nodes because heap size keeps getting decremented. By the time you're done, the tree is empty. Actually, the tree will have one node in it because n minus 1 times you're going to execute this. So when you're done, the tree will have one node in it, and it'll be the smallest value, and it'll be in position 1. Trace this on examples and implement in Java or C, or any other language you like. How many would like to have that as sort of a bonus programming project? Surprisingly few. I would have thought that everybody's hand would shoot up, because that's a nothing assignment, guys. There's no way I'm going to give you that. That's a 12B assignment. That's too easy for you guys. Okay, way too easy. Was I excessively harsh? I think it was harsh. That was harsh. Forget about it. Okay, that's exercise. But what do we care about? We mostly care about runtime. So runtime. Runtime is well. We ought to be able to just write it down. There's the cost of build heap, line 1. That's theta n. And then a loop that executes n minus 1 times constant, call to heapify. Now, most of these calls to heapify, huh? Oh, for crying out loud. Thank you. Call to build heap, that's theta n. That's assignment, that's constant. A loop that executes n minus 1 times, so the whole time I was doing this, oh well. That's a constant cost, that's a constant cost. This call to heapify, most of those calls are to the full tree, right? The first call is a tree of size n. Second call is a tree of size n minus 1. Third call is a tree of size n minus 2. But they all run in time theta log n. Okay, so what does that add up to? This is a lower order term. This is theta n, so this is theta n log n. Okay, so runtime is theta n log n. Isn't that a coincidence? It seems like, have you noticed that all sorting algorithms seem to fall into two groups. The two groups are the algorithms, the bad algorithms that are easy to understand. That's bubble sort, selection sort, insertion sort. But they all run in time theta n squared. And then the really good algorithms that have some subtlety, like recursion or something else. Those are merge sort, heap sort, as we're seeing, and quick sort. I don't think we've done quick sort. We haven't done quick sort. I used to do quick sort. Don't ask me how I ever had time for it, but why is that, do you suppose? Can you do any better than n log n? You cannot. So there is a theorem that says you can't do any better than n log n. So this is a kind of a higher level theorem than what we're used to. It's the kind of theorem, or a theorem that I would study in detail in 102 or 201, like sort of the next class after this. Now, I can give you a good intuitive reason of why that's true. The idea is that sorting algorithms work by comparing elements in the array as to their size. And remember, that's our basic operation. Pick two elements in the array, compare them as to their size, and then do something as opposed, when you do that comparison. Usually it's a swap or a sequence of swaps if they're out of order, maybe do nothing if they're in order. So the engine that you have at your disposal to sort an array is the ability to take two elements in the array and compare them to each other. Okay. The family of sorting algorithms that work that way are called comparison sorts. You might think, well, how else are you going to sort? Believe it or not, there are non-comparison sorts. There are sorting algorithms that use other information, and they're in this book too, but I won't get to them. Like I said, I would cover that in 102 or 201. Okay, so for comparison sorts, there is this lower bound. You can't do any better than n log n. Why? This is why. A sorting algorithm is really a searching algorithm, if you think about it. Because what you're searching for is the permutation of the input array that causes that array to become sorted. You're looking for a rearrangement of the input numbers. All right, let's assume they're all distinct. So there's no repeated ones, just for the simplicity of this argument. Okay, well, how many different permutations are there of n elements? You got an array of length n. How many different rearrangements of it are there? N factorial. So you're searching a space of size n factorial. What's the best searching algorithm you know of? Binary search. Binary search runs in time log base 2 of the size of the search space, right? So a comparison-based sorting algorithm is at best doing what binary search does. Because if you compare two elements in the array as to their size, and you establish that either AI is less than AJ or AI is not less than AJ, what you're doing is, at best, eliminating half the search space, because exactly half of the permutations have AI to the left of AJ, and the other half have AJ to the left of AI. So by establishing the correct order of two elements in the array, you can, if your algorithm extracts the most information it can out of that comparison, it can throw away half the search space. So the question now becomes, how many times can you take n factorial and cut it in half before you get down to 1? The whole idea is take the search space, divide it in half, divide it in half, divide it in half, until your search space is size 1, and there's only one rearrangement left. That's the one that sorts. All right, so how many times can you take a number and cut it in half before you get down to 1? Log base 2 of the number, right? Asymptotically, log of the number. So theta log n factorial, that's the theoretical lower bound. But what is log n factorial by somebody's formula? By Stirling's formula, that is what? N log n. So that's where this n log n comes from. Comes from Stirling's formula. That's actually theta n factorial. Okay, that's the theoretical lower bound. All right, so heap sort is a wonderful sorting algorithm. Runs in the same time as merge sort, but it's superior to merge sort. Does anybody see why it's superior to merge sort? I don't know about the constant. Yeah, they're both pretty good. The constant buried in the theta notation, you can always compare those. And that is sometimes the best way to get at that is experimentally. You can get it theoretically too. Space. Is anybody else going to say space? Yeah. Remember, merge sort requires as much memory, temporary memory for doing the merge operation as it needs for the input array itself. Whereas heap sort doesn't require all that extra memory. We say that heap sort sorts in place. So this is a better algorithm. It runs is just as good asymptotic runtime, but much more efficient memory-wise. Go ahead. Average case also has a theoretical lower bound of n log n. Okay, different argument, slightly different argument, but and to see a more rigorous argument, you have to take CS 102 or 201. But average case runtime is no better than n log n. The best case, by the way, in any sorting algorithm is n, right? Because I mean, what did most people do if I said, okay, here's an exercise, go invent a sorting algorithm. Go invent your own sorting algorithm. Most people, when faced with that exercise, scratch their head and say, what am I going to do? Okay, well, first thing I'm going to do is check and see if the array is already sorted. And if it is, then I'll stop. Would that be your first impulse? Okay, a lot of people would do that. I've seen it many times. Okay, that might be wise or not, but if you happen to be right, that's your best case runtime, and that takes time in. So look, any sorting algorithm has to at least touch every element in the array once to look at it and compare it to something. So the best that you can do is n. Okay, so that's runtime of heap sort. That's the answer to part of the why we bother to have these. Now, I guess it's 6.5, priority queues. Okay, so priority queue is an ADT, and this ADT is most efficiently implemented as a heap. So this is my other answer to the why. Why bother to have heaps? We've answered the how, and we already see that heap sort is a pretty good algorithm. That answers, if this was the only thing that heaps were good for, then heap would be worth having. But there's something else that's good for it. So a priority queue is an ADT, an abstract data type. So remember what that is. That's just a mathematical thing. An abstract data type is just a set of operations, a set of states, and a set of operations. This goes back to the first handout, which I did not cover, but it was required reading. I hope everybody read it. It's an ADT that maintains a finite set S of elements. Sometimes we refer to these elements as records. Now, each of these records contains some data, but there's one piece of data that we care about, and that's a special field called a key. Each having a key field. So think of the key as being not an account number, but an account balance. Because the key somehow tells you how important the element is. That's why it's called a priority queue. You want to be able to grab the most important key first. That's the idea behind a priority queue. Certain elements in the collection are more important than others. And just like heaps, there are two kinds of priority queues. A min priority queue, the most important key is the smallest. A max priority queue, the most important key is the largest. So if X is a record, there are a bunch of fields and a key field. And this is a typical element in the finite set, S, that is being maintained. This other data I will refer to collectively as satellite data. So this is some kind of a database. And S is itself a collection, a finite set of such records. Key X, key of X defines the priority of X in S. Okay. Now, remember, an ADT has two things, states and operations. Here are the states. The states are, I'll use capital script S to stand for the states. They are all possible finite sets. So one of these finite sets is a possible state for the ADT. So I'll change the state by changing this set in some way. Eliminate an element, add an element, maybe change a key, so increase or decrease its priority. Those kind of changes are the operations that I will make that will change the state. Those are the manipulation procedures. The access functions, would read off, information like in this particular state, which guy has the highest priority, which guy has the best key, either highest or lowest. So a max priority queue supports the following operations. A min priority queue has different operations. So here are the ADT operations. First, insert. X into S. So that simply inserts a new record into this finite set of records. Max S. This inserts X into S. This returns the element that's the record with largest key. If this was a min priority queue, it would be called min, and it would return the element with the smallest key. Extract max. This returns and deletes the record with the largest key. And then finally, increase key. So if you think about it, compare this to a queue or a stack. So if you compare it to a stack, max would be a peak operation. Look at the top element, but don't pop it. Extract max is like the pop operation. You know, delete the top element and return it. This would, by the way, be some kind of a mixture of manipulation, procedure, and access function. Okay, and then one more, increase key. So, I've got another argument, x. So this, increase key S, X, K. So take the record X and increase its priority to this number K. So increase key of X to K, but only do that if K is bigger than key X. Else do nothing. By the way, I'm pretty sure that the book treats else as some kind of an error condition. So they have a precondition that says K has to be bigger than key X for you to call this. And I say, I disagree with the book on that. Okay, one of the rare instances where I'm willing to fight the book. I would say simply, if K happens to be less than key X, do nothing. It's going to do no harm, basically, in where we use priority queues. Okay, so those are the priority queue operations. You might say, oh, by the way, if this were a min priority queue, I'd have extract min. If this were a min priority queue, I would have decrease key instead of increase key. So there's a sort of a duality. Min heaps, max heaps, min priority queues, max priority queues. So in order to keep consistent with the rest of the chapter, we're going to describe from now on just how to implement a max heap using a max priority queue. I'll just write PQ as a max heap. So I'm going to give you specific algorithms. By the way, it's not the only way to implement a priority queue. I want to separate. A lot of people mix up these two notions. An ADT is an abstract mathematical thing. A data structure is some particular set of structures in some computer language. So there are other ways to implement a priority queue. Like you could just have an unordered array, and you could do all these things, right? You can insert something, and you can find the maximum. That's a linear search, probably, and you can delete the maximum. You can delete stuff from an array. Well, if you're going to do inserting and deleting, maybe it would be better off with a list instead of an array. Depends on where you do the inserting and deleting. Okay, so, but it turns out that the most efficient way to do this, I'll leave it to you to try to think of other ways to implement it. The most efficient is a priority queue. So here's heap maximum. Takes as input an array A arranged as a heap. Precondition is that the heap is not empty. Heap size A is greater than or equal to 1. And this, I'm sure everybody can figure out how to do this. The largest element is always at the root. If you've got a heap, you know the largest value is at the root. So this has just one operation, return. The root is index 1. So return the value at index 1. That's heap maximum. And the runtime is constant. Okay, can't get any better than that. Okay. And then heap delete max. Now this wasn't one of the operations, but it's sort of this is a pure a pure manipulation procedure. Heap delete max A. And again, precondition, something is in. The heap. How am I doing on time? Not too good, huh? So, heap delete max is like one step in heap sort. First of all, do a swap. A1 swap with A heap size. You could overwrite if you want, but at least A1 will still be in the array. So you do this swap of the largest with the rightmost. Then you decrement heap size. So the largest element is still in the array but excluded from the heap. And then 3, a single call to heapify. A1. This is basically just one step in heap sort, isn't it? Do a swap, decrement the heap size, so the larger element is now still in the array but outside the heap, and then heapify. So you now have a heap that no longer has that maximum element. And this runtime is theta log n. Because that's constant, that's theta log n, where n is the number of nodes in the heap. Now I mentioned that, even though that's not an official ADT operation, because it's a pure manipulation procedure. Now, heap extract max same precondition. Heap size A greater than or equal to 1. 8, 9, 10 is very similar. First, save the maximum element. And then call delete max. So I deleted it and then now return it. Return max. Had to save it because delete max gets rid of it. So by the way, this could be an overwrite instead of a swap if you really didn't care to have it around anymore. Okay, so that's heap extract max. Do I have time for the last one? Unfortunately, I don't. Well, I got two more, heap increase key and heap insert. Exercise, rewrite all these algorithms from the point of view of a min heap. We didn't get to Dijkstra's algorithm, and you have homework problems on Dijkstra's algorithms. So what do you think we should do? Okay, I'll give it till Wednesday. We can't go past Wednesday. So that way you'll have a fighting chance to do those Dijkstra algorithms. So homework 8 is going to be pushed back one day. Please take a few minutes to get rid of these papers up here. Please take these midterms and returned homeworks off my hands. If you didn't get your paper, please get your paper. Both papers, both your midterm and your homeworks. I don't want to haul these papers back to my office.
So the problem I had in DFS yesterday traces back to list again, always, every time.
Yeah.
And it turns out to be
Didn't we have a conversation?